So last week, we just finishing about the auto transformer. Of course, we do know the auto transformer is really famous transformer method, and we are using single winding in order to produce the transformer function. Input side and output side, we share a certain part of the number of turns. So we also see that in here, the current in here will be by Kirchhoff's law will be equal to I1 and I2 difference. So in that case, you can see that this current could be either less than the input current or output current, depending on is step up or step down. But the thing is, we can see that this transformer, because we're only using copper wire without any isolation, there won't be any galvanic isolation. But this transformer is simple, easy to do, only look like one inductor to make up the transformation. So last week, we also looking into about the turn ratio. So in here, we have transformer turn ratio. Then we can see that if the holes 1/n here less than 1, that will become step-down transformer. And then I want to see this current, how it relates to the input and output, because this current actually equal to the difference between I1 and I2, right? So that means if this current, say I2 minus I1, is greater than I1, what is the condition? We find that N is greater than 2. So under this case, you can see that this current will be higher than I1 or vice versa. If this current is less than I1, then N will be less than 2. So that helps us to do the design for the transformer. We're also looking into the step-up transformer with the whole term here is larger than 1 becomes step up. And then we looking into the current here, I1 minus I2, this current, we test them to see if we're able to greater than I2. Because there is a step-up transformer, I2 supposedly will be less than I1, but the difference here can be more or less. So we examine I1 minus I2. This I1 minus I2 is equal to positive because I1 is greater than I2 anyway. It's step-up transformer. So when this greater than I2, we come up with N should be less than half. So in this case, you can see that this condition, it gives us some design concept about how the correlation between the winding in here and the winding current in I2. So we did that, and then we also did a tutorial to show how the transformer look like. For this step-up transformer, we're now checking the voltage conversion ratio. And in here, you can see that the turn ratio here, I1, relate to the N3 here. N1, N3 will be 2,000 turns to 200 turns. So that means total number of turns will be 2,200. So we work out the voltage across here equal to 2,200. We work out the power level, which is kVA power level, 1.1 MVA. And then for so that output power, for the input side, we can just work out the current from the input side using transformer turns ratio. We can work out the input current, hence we can get the input power rating is equal to 1.1 MVA. So obviously these two should be equal because we assume there won't be any power loss at the moment for the transformer. And then we also work out that using Kirchhoff's law to this current is only equal to 58. So that's to say for this auto transformer, even the output and input side serve 100 amp, but the overlapping winding only very small current. So that's something we can see the auto transformer quite special. Other people may think, oh, the common winding here, because it share two current, may be even high current, but that's not the case. Because that's by simple Kirchhoff's law, we know that this current is less current anyway. So that's an observation we can see from here. And then we're also looking into the transformer. You see, three-phase transformer will have many configurations, like the Y and delta combination. So that means 2 times 2 equals 4, at least 4 combination. So in here, I show you Y to delta, delta to Y, and also Y to Y and delta to delta. So this kind of the delta and Y connection do have some reasoning behind which one we shall use. The thing is, the transformer itself do have the free winding here. So when we connect in such a way, it becomes star. So you can see that the input voltage V here, the line voltage, when we go to the phase voltage across the winding, the voltage becomes V over √3. So that is to say, if a motor or transformer, if you connect direct online to a transformer, then you can see that the voltage in this winding will be less than the input. So that means for direct online transformer, direct online of motor, the stress will be less. But once the motor become more stable, then we can then using switching to change them into delta. Then in this case, the input voltage directly impress on the winding. So that's so-called the direct online method. We try to use star to delta conversion. So we get some switch there. We can rearrange the switch after the motor becomes stable. So that commonly being used in the industry. So this method has been used in the industry when we don't have the inverter. But today, when we have the VSD variable speed drive, we don't need to do that because VSD also very cheap. But in the old day, or when the power is very, very high, we don't have suitable inverter to do the job, then we can use this kind of the Y to delta startup circuitry. So this kind of Y to delta startup circuitry have been used in the past. But of course, nowadays we gradually move on to using inverter to try that, or some kind we call it VSD. That also common method we use for three-phase transformer anyway. So here will be different kind of connection. So one of the animation we like to use three-phase instead of single phase because for any power level, as I see that when we more than 3 kVA, then we tend to use three-phase system. Because the three-phase system, automatically inside the three-phase will be balanced, then that will be less demanding for the power distribution. You can also see that for the rectifier in here, for three-phase rectifier, compared to single phase rectifier, we're doing this. That's single phase. Then if you want to rectify it, then we will fill up this gap. That would be really demanding for the filter LC component. But if you use three-phase system, then we can see that all these are being so the ripple here are only small area require the LC to fill up. So that will be less demanding for the LC filter system. So that's why this kind of system, for any high power, more than 3 kVA, probably we tend to use the three-phase system. So the configuration will be like that. When we have transformer in such a way, then we can put them together. In each of phase will be in this arrangement. So the summation of flux equal to 0 because you can see that the 0 degree, 120, that will be 240. So when this add up together, then become symmetrically cancelled out. So all the flux in here being cancelled out will be approximately equal to 0 anyway. So for the winding here, the phase A, B, C. So for example, like we have primary winding here. The secondary winding usually put on the top. Secondary winding here. Between them, of course, there will be some insulation, like passive insulation, to protect from any punch through between the two voltage. So in here, you can see that another possibility to do the three-phase transformer will be E-core, which will be like that. So you can see that the primary and secondary all putting together, but it's not one on the top of each other, but actually will be like this. So we have the inner winding, usually with primary, outer winding will be secondary. They try to wrap them on top of each other in order to have better coupling. When the two windings are closely together, then the coupling will be much better. So that means, although in the textbook, you can see in many textbook, you have the primary here, secondary here, right? But that's not the case. The coupling here will be poor. Yeah, because you can see that there's a lot of fringe field appear between them. We don't like fringe field because you contribute to leakage inductance. But if you can see that if you're putting the primary and second together, all the fringe field will also link between primary and secondary. So that means the coupling will be much better. So for pedicle transformer, we'll do it as such. And then we're also looking into how we can able to use single-phase transformer to make up the three-phase transformer. So that is one of the configuration. So you can see the three-phase transformer, and then notice the dot rotation. And then the other side will be all connected. That will become a Y connection because you can see that that's a Y connection. For all the Y connection, we got a common point here. And then for the delta connection, they all are connected to each other, like a delta. There isn't any neutral. So then N, you don't have any N here, but in here we got the neutral. N is mean the neutral here. So, but for system that if the three-phase highly balanced, the neutral voltage will be negligible, will be equal to 0 anyway. So that's the case. The neutral, we don't need a lot of the way to be careful. But however, if there's harmonics, then you see the harmonic current, especially the tripling, the third harmonic, ninth harmonic, tend to appear in the neutral. That will be another topic for more advanced machine design anyway. But for basic electromagnetic, then we can tell you usually the neutral current, we tend to make it small when they are balanced to each other, when there isn't any harmonics. So the rest of them will just tell us why we like to use single phase, because we can able to cost effective, because we use single phase transformer, we have three-phase transformer. For maintenance will be much easier because we don't need to check or replace all the three transformer. If any one of winding is broken, we can just replace that particular transformer. And then the balancing of load will be easier because you can fine-tune each of the phase carefully. But if we use three-phase transformer, sometimes the input line is not really highly stable or highly balanced, we can't do anything. But in here, for using three separate transformer, we're able to fine-tune slightly, maybe add one turn in certain phase in order to adjust the voltage properly. And mass production usually will be cheaper. In here, we can have mass production for three single-phase transformer. Whenever we use mass production, the total cost will be lower. So instead of using a large three-phase transformer, we need to make the whole transformer. We cannot repair the transformer so easily because if that's broken, usually for the maintenance people, we replace the whole transformer. So that is to say, using single phase, we can just replace one third of the unit. That would much lower cost in long run. So, and lastly will be the transformer losses. I think you all learn about that. Basically, we got two major losses for transformer. One will be hysteresis loss. All the BH loop is not equal to linear line, but form this kind of BH loop. We call it hysteresis loop. So that the area enclosed by B and H is equal to the power loss or the energy loss. So in this case, if we one period, then the BH will go through this loop. In this case, we can see one energy loss within one period. When the frequency getting higher, then it just proportionally increase in such a manner. So that's why I can see the hysteresis loss are directly proportional to the frequencies and also relate to a constant. And the B is with an index here, exponential index of around 1.5 to 2.5, depending on the material. So typically it will be 2, but can be anything between here. So the other two will be the other constant anyway. This constant highly relate to the material, so usually that can be provided by the manufacturer or you can measure it. Another loss is eddy current loss. I think you all know eddy current. Whenever there's a metal material pass through, it generates the electric current inside metal material. If that metal material is conductive material like the iron, then you create the iron loss, or so-called the eddy current loss. So this eddy current loss will be looping in such a way. When a current pass through, using right-hand rule, we can see the current looping around that flux. And then you can see that if that current looping in here, then they will create the losses. Because whenever there's current, the current will flow through this iron called the iron, will create a more look-like power losses. So that's why for transformer, we usually put the lamination like in here, number of the lamination plate. So for low frequency transformer, 60 Hertz, then we put many of the transformer plate. You can go home to check your transformer. You can see many of this kind of the layer. And each of the layer, for example, like an equal transformer, you can see many of this kind of the layer, right, in the transformer. And then together with this kind of the plate. So with many of them, we can insert into the transformer bobbin, the core, the so-called former, and then insert to them, and then you can put the winding. And each of these one, we call it laminated. So there were a little bit of isolation material, maybe paint, maybe enamel in order to isolate the metal conduction between the layer. So that's what we're trying to do. But the thickness of this one, we don't have thickness here. It's quite important. I think you all heard about skin effect, right? Skin effect, when this thickness is less than the skin depth, usually the losses can be small or could be negligible. But the skin depth are related to the frequency. Higher the frequency, the smaller the skin depth. In this case, for 60 Hertz, then our skin depth will be quite thick. So that means you can see that the metal lamination are quite thick, probably in the area millimeter. But when we go for high frequency, then we can't use the lamination. No matter how good lamination is, you can't make up down to 0.0 something millimeter. That would be too complicated. Then we have to use ferrite wire or powder iron core. So that's the norm. So now then we got, so eddy current loss are proportional to F square and also B square. So I'm usually using the pit in here. Many textbook or many reference use pit B field here, pit B field. Of course, with proportional constant. Of course, some literature, they may use RMS here and merge this one into here. But I found that most of them tend to use pit B field because the pit will be responsible for the highest amount of the losses. Sometimes if the B may not be purely sinusoidal. So that is to say, you're not able to use RMS value to estimate about the core loss. So that means pit value will be more reliable to calculate the losses. So the total losses will be the hysteresis plus eddy current loss. And then another method, you can see that we tend to use a lookup chart to take out the losses because you see all these formulations are actually from measurement, so-called empirical formula. So we use many measurement data fit in this curve to get the Km parameter. So that means that's using measurement to get the parameter. So also in here as well. So, but another method will be the manufacturer will present them in terms of the graph. So in here, you can see that the losses will usually per unit volume, sometimes per unit kilogram, depending on the manufacturer. Then the one of the variable here would be the magnetic field density, how many Tesla. Then if you know your design of the B field, how many Tesla, and then you also know the frequency operation, because your frequency dependent, you can see that in here, high the frequency, high the losses. And then you also temperature here, also temperature dependent. So you can see 2 lines here for 2 temperature. So when you get all the parameter, then you can using lookup chart method to get the losses. That's also really reliable. Although people may say, oh, why don't I use formula? It look like more reliable. That's not the case. Even though formulation are provided by the manufacturer, where they get it, they use the data and then using the fit-in curve to work out the formulation. So they are all not really accurate anyway. So I find that for magnetic power losses, usually the accuracy is not really secure. So even though 20%, 30% already quite good. Of course, in the future, if we're able to model it properly, we can able to have more accurate measurement or accurate estimation. So here will be one really quick example, show us how to use the loss calculation. So basically, if we are given with that, for the hysteresis loss component KH is equal to this parameter, frequency 50 Hertz, and the maximum B field 1.2 is potential M equal to 2. For the eddy current loss, we got another KE constant. We got B field, of course, will be the same because for the same magnetic material, frequency also the same, the thickness of the lamination, and then it's 0.01, yeah. So now then we calculate losses. We just pump everything into the formula. Then we can get hysteresis loss equal to 0.11, 0.14, and the eddy current loss equal to 0.36. Total loss will be summation. So this method don't have anything special, just to show you how to put them together, how to add up all the losses together. So for experimental testing, we usually look up table to get the property design. we can never ensure that this formulation will be accurate, because even though these formula are provided by the manufacturer, they only using log table to feed in this curve to you. They never guarantee to be accurate. And also this curve also from the manufacturer, then there will be limited range, only give you this range. This only within this range will be reliable because they did the measurement. Beyond this range, although they look like a straight line, don't tend to think they are continue become a straight line. It can be anything because they haven't done the measurement. So that means for reliable design, only use this range. If you find that this range is beyond your design, you choose another core. For instance, your B field say is more than 3.7, right? Then probably you cannot use this material. You need to get other material. If your frequency is more than 400K here or 500K hertz, then you cannot use this material. You need to use more high frequency material. All depend on what have here could be reliable. Anything beyond, don't think about the curve will be straight line. Don't use exponential. Yeah, because the range of this kind of the data feed will be really limited. We never can guarantee how accurate they are. So for different material, you try to look up from the material manufacturer data. They will have this chart for you. So each one will be for what frequency, what B field range, what temperature. That's the thing you look for. Because we always try to look for lower losses. So that means you need to do some pre-calculation for the design to see what kind of losses it could be. And then that's only core loss. And then we also have the copper loss. Copper loss usually will be equal to the I square R from the copper, right? But it's more than that. So we don't try to cover too much for you for the copper loss here. The copper loss will be another complicated topic because there will be skin effect on the copper. There will be additional losses. So in here, I just only show you the copper loss. Sorry, the core loss. So here will be one of the tutorial. So we say if the B field is 200 MT, 100 degree, frequency 100K, and then the volume of core with linear outer diameter equal to this one, and calculate the losses. So when we have this geometry, 20 cm, 30 cm, and thickness 5, we can actually estimate about the volume by using simple geometrical formula. And then for 200 MT, 100 degrees C, 100K, we can therefore look up from the chart in this location. We can therefore work out about the losses per unit volume. And then we multiply volume, we give us the losses. So we all use this method. You may ask the manufacturer to give you the formulation, like K, B square, F square, something like that, but they are not reliable anyway. If they give you, then they will limit it to a certain range. But you can also use a lookup chart to see what the power losses. So that's a typical way to do that. There isn't any theoretical formulation to govern all the power losses. They all so-called empirical formula by measurement and feed in data. So remember that there's no theoretical calculation to calculate the loss. It's not I square R, right? Resistive loss, we don't have that. We only have all of them are approximation. So anyway, that finishes us about the chapter for transformer. Finally conclude that then the transformer, we can use it as an impedance, which is quite nice to do that. And we also learned something about auto transformer, which we see that the common shredded winding could be something special. We can reduce the current. And then we also know something about the transformer, three-phase transformer parameter. We also need to know the dot notation. When we connect a number of transformer in parallel series, we got a lot of the new method of the voltage conversion ratio by using limited number transformer. So in your homework, I can ask you to do certain combination to build up a big table to see what kind of transformer conversion ratio look like. And then for each of the case, you can also see that the current will be different. For instance, you can see that when you go back to here, when we have different transformer connected in such a way, so if this is a power rating for transformer, you give you this current rating. And this transformer, you give it this current rating. Because transformer ratio 1 to 3, 1 to 2, in theory, this current is different from this current. When you connect them in series, you force these two currents become equal. Then that means the actual power rating for the transformer could not equal to summation of each one. if these two transformers same power rating. So you need to, when you do your homework design, you need to reassess about what kind of power rating it will be, what kind of output current it will be. Of course, the current, we have two current rating here. They connect in series. You're going to use the lower current rating because for safety, right? You won't use the larger current rating. So that's why from this exercise, although it looks simple, but you need to also work out the power level, the current rating to see would there be any increment or decrement for the power rating when you put in two transformers together. Okay, any questions? If not, then we finish this chapter. So finally, the conclusion, and then we also have the reference, so which many of my material could be from these books, and also from here. This kind of material is really commonly well available. So you can search for many websites. So like this website, you can also see some of the people to work on the design. I do have a textbook for these three, but it's too expensive to buy one, a few $100 each. So probably it's not wise to do that. Just use my notes will be good enough. Okay, any question? Transformer is very simple topic. I think you're highly confident in that. But now we give you a quick revision so that you know how the undergraduate or junior postgraduate to look into the transformer. Anyway, okay.